what is the radius of convergence of this series? And for what values x does the series converge? Now these look to me at the beginning as if they are exactly the same question, but in reality, you should not be tricked by this, and there is a certain subtlety with the second question that we will deal with a bit later on. Regarding this series, it is a bit unique. I would like to take a moment to draw your attention to the fact that the series has two parameters. The first one is n, and the second one is x. Well, in a sense, it has one parameter, which is x. And in the other sense, there are two variables. So this series depends on x. Its convergence depends on x. Because I could choose x to be equal to 0. If I choose x to be equal to 0, I'm telling you 100% that this series will converge, because we just have zeros, right? And if you choose it to be a big number, as it looks like, I think it will diverge. But that is the naive, it doesn't have to be naive, just the raw review that we give, the initial outlook of the situation. This is how it looks like. Now, let me start by introducing the machinery you will be using to tackle this problem, namely the ratio test. So the ratio test provides a criteria for the convergence of, well, the absolute convergence of a series. And it tells you this. So you take an element of the series, one term, you divide it by the term that's preceding to it. So you take an plus 1, you divide it by the preceding an, and you take the limit as n goes to infinity. Now this ratio test tells you that if your limit is less than 1, then you have absolute convergence. If it's greater than 1, then you have divergence, and if it is equal to 1, then it is inconclusive. Then perhaps it is a good idea to take a look at this limit and see how it would look like for our problem. And so what I'm going to do now is I will take the n plus first term and the nth term. This is clearly the nth term. I don't think this requires an argument. I hope. This does not require an argument. And this is the same term, but instead of n, I will write n plus 1. N plus 1 minus 1, this is n. Okay. Now I want to remind you that these two are absolute values. So in a sense, we won't be in need of these alternating symbol counterparts. So we don't need the minus 1 to the power of something. We know the minus 1 to the power of something will either give us 1 or minus 1, but in the end it doesn't matter because we're looking at the absolute value. We're looking at the magnitude. So let me write this without the symbols, the minus ones, I mean. And now notice that on top we have x to the n plus 1, and on the bottom we have x to the n. It seems that these two will cancel out, and we will have an x still remaining. Now this n plus 1 is in brackets, let me emphasize that. And write the x that we had, and I'll multiply this by what we have for n. On the bottom we have 1 over n cubed, and on top we have I know this looks weird. Now it doesn't. And since this is a fraction of fractions, we can flip the fractions, and therefore this will go downstairs and that will go upstairs. And now the limit is taken as n goes to infinity. If n goes to infinity here, it seems that the numerator and denominator are growing at the same speed. And therefore this limit has a value 1. And so this whole expression will be equal to the absolute value of x. Now, I want you to recall that for the ratio test, in order to to satisfy the convergence criterion, we would like to have our L, our limit, to be less than 1. And this is the point where I want to redirect you to the very beginning of this video, and we were talking about this parameter x, which we can control and we can change to our liking. And here, we will use this restriction that we have on L to find a certain range of values for x. In other words, we would like L to be less than 1. I think we can agree on this. And on the other hand, L is equal to the absolute value of x. And therefore, the absolute value of x needs to be less than 1. Or in other words, x needs to be in the interval from -1 to 1, the open interval. And in fact, this answers the first question we have regarding the radius of convergence. But we need to be careful. First off, the radius of convergence in this case is 1. Let me explicitly write that out. The radius of convergence, which is usually denoted by rho or sometimes denoted by big R, is equal to 1. Because in a sense, that is the value for which you have this freedom. And then perhaps you would, as I initially mentioned, assume that we are already done with the question and you would move on to do other questions. But we have to be careful with the edge cases. This is what I would like to call them the edge cases. Let me delete that. And the edge cases happen precisely at the edges of the interval. No surprise. So let's take a look at a series at the value x is equal to 1 and see what happens. Let me start with a new frame here. And there is a theorem which we will be using. And this perhaps gives you a guess on what we will be dealing with right now. That is an alternating series. So to find the series that I get for x is equal to 1, it is enough to plug in this 1 here. And I will leave it as it is for emphasis. And then write this as follows. I mean, we should agree on the fact that 1 to the n is just 1, and we can pretend that it's not there. I hope that it's not too difficult. So what we have here is what's called the alternating series. The reason why it is called the alternating series is because it alternates, no surprise either, I'll write the first few terms just to make a point. And so on and so forth. And when we say alternating, we mean that in terms of the sign. So it alternates the sign. This is such an alternating series. So let's take a look at the theorem, see what it says. It says that if you have this series AN, you would like to take a look at Bn. In our case, Bn is the part which does not alternate. So this is the part that alternates in the series. That is the part that doesn't. And therefore, I can confidently write 1 over n cubed as the part that doesn't alternate. Now, for this Bn, which we've found to be 1 over n cubed, we would like to check two things. The first thing is this limit equal to 0? And the second thing is the sequence Bn decreasing? And the answer to both questions is positive, and therefore this is convergent. Let me omit the technicalities and only include the parts which are technically relevant. Now again, Bn is the part of the series which does not alternate. So it's the, how do you say this? It's the pure part that doesn't really represent the sign, but rather represents the magnitude. So that's about it. Now we still need to take a look at the case of x is equal to -1, because that is the other edge case. I take the exact same series. Instead of I plug in -1, be careful with the brackets. And do you know what we will get here? You get -1. The reason for that is we are multiplying in a sense by two numbers, -1 by two numbers that are right after each other. So for example, if you multiply, one of the numbers is going to be even and one of them is going to be odd, because there are two consecutive numbers. So one of those is even, another is odd. And if there is one odd power to the -1, then we will get the negative sign. And this turns out to be the case for all of the terms. Could also write down the following. I'm just too lazy to write it. So you could write this as and this is of course always equal to 1, and that is of course equal to -1. So this is why you get -1. But that is a rather silly computation. So let's not do that. And now I'm here, and since I have the minus sign, why not put it in the outside and try to focus on this? Now it turns out that this very series needs some sort of machinery as well. So give me a moment. So this is the piece of machinery. That's the integral test. Now, avoiding the technicalities, it says that if you have some sort of sum that looks like this, it's always going to be smaller than the integral, because in a sense, the sum is discrete and the integral is continuous. So you can always bound the sum by the integral. And this is effectively what I'm going to do right now. I will not do this for the negative sign. I don't even care about the negative sign. Because I'm looking to find convergence and divergence. So it doesn't matter if it converges to a positive or a negative number. Now, this I could write as an integral from n is equal to 1 to n is equal to infinity. Well, it's a limit in reality. There's no such thing as n is equal to infinity. I should write this precisely as a limit, but I hope you'll be so kind to allow me to do this for now. And we are integrating 1 over n cubed dn. Now I imagine this is not by any means a difficult integral to compute. This should give us minus 1 over n squared times 2. Yeah. I hope I haven't forgot all of my integration abilities, and I hope you haven't either. But I'm guessing it will be too inconvenient for myself as your instructor here, not knowing how to compute an integral. I think that would be very inconvenient for you. So this is going to give us some number. It is actually going to give us 0 minus negative 1 over 1 squared times 2. Gives 0 plus 2, which is equal to 2, which is less than infinity. I don't really care about what happens. All I care about is that it's finite. And if it's finite, then this also converges. And this is amazing because now, here's what I can say. Then this series, which I forgot and I don't have on the top of my head, converges for x in minus 1 to 1. And that should be more than sufficient for the goals we would like to achieve. I know this has been lengthy. We've utilized 3 theorems so far. I think it's a matter of practice. If you get used to them, it becomes easier to think about and to utilize and to summon, so to say. So if I have this series and I'm stuck, I don't know what to do, I'll try this, I'll try that. And this is really what practice does. It cements the idea. You don't have to practice it and you don't have to look it up. You just know it. And that's what happens when you really put rigorous training in whatever you do, not just in mathematics. And I hope that this is a philosophy that you can take on and transfer to many other things in life. But again, I'll stop before we diverge enough from the main theme of these tutorials, which is to teach you some mathematics.